So here we are on the Python track, and we want to explore cryptography, figure out a little bit about this RSA you keep hearing about. What is that? How does it work? Well, it's written about all over the place on the web, so I don't need to be redundant with all that. If you read Sarah's book, she's only 16 in high school or something trying to improve on RSA, and that gets her very famous, and that may be how you first heard of RSA. I don't claim to know, but back in going back in time, here's about how she's famous. Uh, Good book, by the way, In Code by Sarah Flannery, with some help from her dad. She uses Mathematica, and our purpose in this clip is to show that even lowly Python, which doesn't have such high-level math built into it, is a doable proposition. You can really understand it here. Now, in the old days, um, when ships were king, it was pretty easy to exchange your symmetric keys, but later during the Cold War and everybody's kind of more in this kind of twilight zone, you got to find Alice, give her some secret message. And I'm paranoid about Eve because Eve tends to sniff packets and, can get in between me and Alice. And I don't even know Alice that well. Well, those were the dino days when symmetric keys ruled. But now we have this public key cryptography algorithm, which based in current mathematics is pretty secure still. I always explain it in terms of a clock. It's a one-way clock, and you know the diameter of the clock. Um, and I'm happy about this because I know it's secure. I can raise my exponent, raise my plain text to an exponent, go partway around the clock, and then because of a certain secret, my friend Alice is going to go the rest of the way around the clock. She has her secret decrypt number, and she's going to know what I want her to know, and I didn't have to go through an intermediary. So here we're showing, I used this actual groups PY in my very first clips about learning Python and teaching Python if you're a math teacher. And we use this P object in those clips to introduce rib syntax, which is where you're able to override the meanings or overload the meanings of some basic syntax like multiplication syntax and addition syntax. So we're exploiting that here. We're going to run through some tests, drawing from groups, and we're going to look at the totatives of a number as a group. It means we're going to do all the possible additions and multiplications on these small finite little groups. So we start with the totatives of 21. If you remember, the totatives are the numbers that we're going to use a table kind of code. It's another free thing we get with groups PY. We're going to look at the totatives of 21 and the totatives of 17. Now 21 is not a prime number, but it does have totatives, numbers less than 21 with no factors in common with 21. And we're going to multiply those guys together and get a multiplication table. And this is kind of a group theory thing. We're going to see that there's closure, associativity, there's it might be an abelian group. Actually, it is in this case. Every element has an inverse, meaning something it can combine with to give the identity. In the multiplication space, that would be called 1. In addition space, we call that 0. So now we're looking at 21, and you can sort of see there was closure there. Nothing jumped out at us as being outside the set. And this is exploited because in Miller-Rabin, we first generate some probable primes, multiply those, get a composite. But this composite n is very like a prime in that almost everything less than it is totative. And basically we're going to be raising some message, my secret for Alice. I'm going to raise it to a power, and then Alice is going to keep raising it on around the circle back to where the message pops back out again. That's her secret to do that, even though I know her public key. Now, when I tried to demonstrate what happens to 17 when I add, I found out that my P object, or class definition template, has no addition method. So I thought I'd put that in and go back and run this test again. What I'm showing here is that 17 being prime has closure and so forth, not only for multiplication but for addition as well, once you permit 0 to join the set. And that's what we call a Galois field. It's it's a finite group using a prime number and its totatives. And every number under a prime is a totative. That's what it means to be prime. So here, when we look at 17, it's a little bit too wide, but going down, look on your left side, you've got all the numbers from 1 to 16 are going to be there. Here we go. So anyway, what you're going to want to do is probably from here is build a powers table where you're taking totatives and just raising them higher and higher powers, because that's what it's like to go around this clock, this sort of Eulerian clock, where your private message, your secret message to what you want to be a secret message to Alice is maybe converted to hexadecimal, and then you raise it to, say, the third power. You might have to chunk it out. You raise it to the third power modulo some n, which is the diameter of your clock. And from there, you raise it to the third power modulo n, like I said, and that's your C, that's your cryptic text, and your ciphertext. And then that thing is going to get raised additional powers once Alice gets it. See, on Alice's end, her secret is D, and she's going to raise my ciphertext to her D. And because of Euler's theorem that a base raised to the totient of n is going to give you 1 modulo n, because of that we're able to sort of get an exponent of 1. And an exponent of 1 on anything is just that thing itself. So m starts its orbit going to the eth power, and then we end up going to the basically what amounts to the first power once we multiply e by d. The way we get d, by the way, is we use an extended version of Euclid's algorithm, which I also introduced in the very first videos about Python for teaching math. Because my goal would be, as I was saying, Sarah Flannery, she's 16, she's using Mathematica, very high end compared to Python in some ways. But she's understanding and possibly improving on. That turned out maybe not to be the case, but it doesn't matter. She completely understood this material. So with Python at our elbow, a goal for this curriculum is certainly by the time you're finished with high school, you kind of have an idea of, you have more than just an idea, you have a pretty intimate idea of what's behind RSA, how it works, why it works, and what kind of problems it solves between Bob and Alice and Eve. So that's the Python way once again.